Hi, my name is Matt Ozales and I'm an RF engineer at Keysight Technologies. I've been designing RF and microwave power amplifiers for the past 12 years, and in today's talk I'll go through some of the basic modes or classes of PA operation, and I'll also show how to build a nonlinear device model which will allow us to design a power amplifier using basic theory. And then I'll implement my design in a circuit simulator to demonstrate each class of operation, and I'll even share my workspace with you at the end so that you can try out everything on your own. Now, even if you're an experienced designer, I think that you'll find this presentation valuable because realizing what it takes to achieve theoretical operation can allow you to pinpoint the areas where your device or circuit falls short of the ideal case. And ultimately, this approach can help you to reconcile the disconnect between theory and practice as it relates to PA design. So what are the basic classes of operation for an RF power amplifier? Well, the key is that power is dissipated in the device whenever voltage and current exist at the same instant in time. So if we can reduce the amount of time that the device has current flowing through it, there's less overlap in the voltage and current waveforms, which leads to higher efficiency. So as we move from class A to class AB to class B, we reduce the amount of the RF waveform that conducts through the transistor and get higher efficiency by doing this. So to illustrate the concept, I'm going to build a simple device model, and then I'll use this to design a power amplifier, which operates in each of these different modes. So let's talk about what a transistor is from a power amplifier designer's point of view. For any type of amplifier, a transistor has to provide some type of gain. For example, it might take an input voltage across a resistor and then multiply it by a transconductance to give an output current. And this is, of course, a model for small signals, and for most types of linear amplifiers, this is good enough for design purposes. But for a power amplifier, we'll also need to consider the large signal region, and this goes beyond the simple linear gain characteristics of the ideal source that I'm showing here. So first we need to model the nonlinear transconductance. This is the mechanism by which the transistor turns on after some threshold voltage is exceeded. And it's important to model this because large signals will tend to cross over this threshold region, and that will rectify the input signal. In other words, it will turn off the transistor for part of the waveform cycle. And this is actually the mechanism that PA designers exploit to change the class of operation. And at the output, there's a knee voltage where the transistor enters a saturation region after some threshold is exceeded, and ideally this is near zero. And this is important to model because it limits the load line, which is set by the external load impedance presented to the device. So the load defines the trajectory of the voltage and current swing on the transistor. So the voltage and current are forced to assume values which are valid points on the load line of the device. Now, in real transistors, the turn-on portions of these curves are either exponential or square law in nature. But to realize the classical power amplifier waveforms, these regions really need to be idealized, which is part of the reason that it's so hard to achieve this ideal operation in practice. But it's pretty straightforward to implement these functions in the circuit simulator. So for the linear gain block, I used a voltage-controlled current source component, while for the nonlinear blocks I use components called symbolically defined devices. And these allow me to relate the input and output through an equation. So for the nonlinear transconductance, I actually used an if-then statement to rectify the input signal. So if the input is greater than 0, the output just tracks the input, while if the input is less than 0, the output just stays at 0. And to model the knee voltage, I used the symbolic device to realize a reverse bias diode. So all I did was type in the diode equation here, and I also mathematically offset this so that the diode itself turns on at exactly 0. And doing that sets the knee voltage also to 0. And so if the voltage waveform goes below 0, this diode turns on and steals the current, which basically shuts off the device. So depending on what type of device you're using, this may be what happens physically, but I think the more important thing here is that this function provides a mathematically continuous way to go from the saturation region to the off region, which helps with convergence in the simulator. Okay, so here's the device model in ADS, and it has those blocks I showed you, plus a few other things like parasitics. At the end of the presentation, I'll show you how to download this workspace so you can play around with all of these parasitics and things like that yourself. But for now, I'll just run a DC simulation on the ideal device, and I'll sweep both the input and output voltages. And so from that, we can actually observe the large signal nature of the model. And this is the exact set of characteristics that I was looking for. So we have a perfectly rectified transconductance and a flat set of output curves which turns on at 0. Okay, so now that I've got a nonlinear device model, let's talk about how to go about designing a power amplifier. Now, I like to express P out in terms of peak-to-peak signals because this allows you to separate the DC term from the RF term. And from here, what I want to do is draw a load line on my DC curves, which will define the ratio between the peak-to-peak voltage and the peak-to-peak current, and this will ultimately set my maximum output power. So what do I need to know to do that? Well, if I specify a knee voltage and a quiescent DC bias point, then I can assume that the voltage will swing symmetrically around the quiescent point all the way to a point called Vmax. Well, the current will swing around this point, but it won't necessarily be symmetric. So the assumption I'm going to make is that once the current reaches zero, it will stay at zero as the voltage swings up to Vmax. And using these assumptions, I can build a load line model based on knowing just two DC points, which will even allow me to construct sinusoidal RF waveforms from just this data. And from those waveforms, I can extract even more useful information about the PA. For example, I can calculate efficiency directly from the time domain waveforms based on the dissipated power. Okay, so I implemented these equations in ADS to build a very useful load line utility which can extract a bunch of good information for any given device to help you design a power amplifier. And this tool works for any set of IV curves, so if you have a real device, you can apply it there too. And again, at the end of the video, I'll show you how to download the project so you can test it out yourself. Okay, so let me demonstrate how this works on the ideal set of IV curves from the transistor model I just built. So here are those curves, and all I need to do is put marker 1 on my knee voltage and marker 2 on my quiescent point, and then everything else is calculated magically using the design equations. So as I move the marker, all the graphs and numbers update accordingly. So the first mode we'll design is Class A. Now from the sweep I did earlier, my max current was about 500 milliamps. So I put marker 1 on the knee voltage at this current, and then I set my quiescent point marker 2 to be 250 milliamps and 5 volts. And that gives me a load value of about 20 ohms and also a maximum output power of about 28 dBm, a maximum efficiency of 50%. So that's Class A. And we can also tell that because the conduction angle is 360 degrees, meaning all of the waveform conducts. Now let me change my quiescent bias point. Now if I keep the same voltage but move the current lower, the conduction angle decreases and the efficiency increases as the current waveform gets rectified. So the small signal gain is still the same, but the large signal gain drops, and what I mean by that is the amount of gain that happens at the maximum load line swing that I'm showing here. So the potential to achieve the output power is still there, but I need to drive the device harder to get that power. And this is Class AB since the conduction angle is between 180 and 360 degrees. Okay, so let's move that bias point all the way down to the threshold while keeping the voltage bias the same. And this is now Class B operation. Both the small signal and the large signal gain drops by 6 dB because only half of the input signal conducts. And this is shown also by the conduction angle being 180 degrees. And in this mode, my efficiency goes all the way up to 78.5%, which is the theoretical maximum value. Okay, so all of this so far is just based on the DC curves from the device and the PA design equations. So now I'm going to run a large signal harmonic balance simulation on this device to see if there's agreement between the predicted values and the values from the equations. So I've set this up to do an input power sweep on my model from -15 to 20 dBm, and I'll set the bias point at the input and the load line at the output with variables, and now I will run the simulation. And in the data display, I can change the input power with a slider and look at the time domain voltage and current waveforms, and I can also look at the actual RF load line, the rectified input signal, and the complete power compression curve for all of the input powers. So as I increase the input power to get to the point on the curve where the PA begins to compress, notice that I'm getting very close to the values that I predicted from just the DC curves and the design equations. And if I increase the power beyond the point where the load line hits the knee voltage, then the waveforms start to limit from the diode, and the power drops. At the input, also the signal's starting to become rectified and the duty cycle drops as well, so we're leaving Class A operation in that case. Okay, so now let's try for Class AB mode. So I'll go back to my schematic, and here I set the quiescent current to be somewhere in between the Class A and Class B bias points, maybe around a half a volt or so on V1. Also, by definition, short-circuit harmonic terminations are required for this mode to maintain a sinusoidal voltage waveform, so I added a high Q resonator at the output to achieve that, and then I'll rerun the simulation. Okay, well, notice that the compression curve is now quite nonlinear, but once I adjust the input power to account for the effective gain drop, again, the results are in line with what was predicted in the DC equations. Now, one effect that the resonator seems to have is to tweak the fundamental load just a little bit, and that's going to give me slightly higher gain and lower power than I originally predicted, but the efficiency and overall output power are still quite close. And now finally we'll implement Class B mode by simply setting the input voltage in the schematic to 0. And this will initialize the PA so that exactly half of any RF waveform is conducting. And I'll rerun the simulation again. So now the PA seems to be linear at backed off powers, but just as predicted, we've dropped 6 dB of gain, so now there's only 10 dB of total gain. And the PA still has a compression characteristic, which is of course due to the load line hitting the knee voltage. But at this point where the load line just hits the knee voltage, notice that we do indeed get the predicted 78.5% or so value of efficiency. Okay, so we've just scratched the surface on these ideal modes of power amplifier operation. And although these modes are highly idealized, I think that understanding them will make you a better PA designer, because knowing what it takes to achieve this ideal operation can help you to understand specifically what's preventing your device or design from getting there. Now, of course, there's a lot more to learn that I couldn't possibly cover here, but I've included it in an ADS project which you can download for free at the link below. And in that project, I put an example of the interactive load line generator working with a more realistic set of DC curves. It's actually for a CMOS device. But you can use this with any other device too, and this will help you get started with your own design. And the workspace will also allow you to change parameters within the model that I built to see what happens when the nonlinear pieces become more realistic. So if the knee voltage is no longer 0, what happens? And I also have the option for you to add in RF parasitics to the device and see what happens at higher frequencies to the performance. Now for me, seeing how these ideal cases change and degrade once more realistic parameters are included is really valuable, because it helps to explain why it's so hard to achieve the textbook efficiency values with real devices. And adding parasitics made me also really appreciate why a load pull is so valuable for high frequency design. And to help you see that too, I've put in a simple load pull template so that you can even run a very basic load pull on the device model I have and change the parasitics to see how that changes your contours. So there's lots more to learn about in the workspace, and you can find that at the link below. Thanks so much for watching.